Hello everyone, we are going to talk about kinematic constraints. The following assumptions make it possible to simplify the process. The plane of the wheel always remains vertical and that there is one single point of contact between the wheels and the ground plane. There is no sliding at the point of contact. That means the wheel is only under conditions of pure rolling and rotation. The first constraint enforces the concept of rolling contact. The second constraint enforces the concept of no lateral slippage. Fixed standard wheels does not have a vertical axis of rotation for steering. The motion is limited to the back and forth along the wheel plane. The point A in the figure indicates the position by a distance L, and an angle alpha. Beta is the angle of the wheel plane relative to the chassis. This angle is fixed, and theta is going to be our angular velocity. The equation for the rolling constraint enforces that all motion along the direction of the pure rolling at the contact point is going to be appropriate to amount of wheel spin, so there is no slipping. The equation for the sliding constraints enforces that the component of the wheel's motion orthogonal to the wheel plane must be zero.
Now about the steer standard wheels. This type of wheel has an additional degree of freedom. The equation of the constraints are the same as the one seen for fixed wheels, but in this case, beta varies with time. Caster wheels are able to steer around a vertical axis, but this axis does not pass through the ground contact point. There is this the offset. The rolling constraint is identical to the previous equations, but there is a difference in the equation for the sliding constraint. The offset has to be considered, so that any motion orthogonal to the wheel plane must be balanced by an equivalent and opposite amount of caster steering motion. This kinematic model involves to combine all of the kinematic constraints. We have that N is the total number of wheels, NF is the number of fixed wheels, and S is the number of steered wheels, and NC is the number of caster wheels. BF contains the orientations of the fixed wheels. BS contains the steering angles of the steer wheels, and BC contains the steering angles of the caster wheels. In this equation, we have the pure rolling conditions. This J1 is a matrix, is derived from all the kinematic constraints. The matrix J1F has the size of the number of the fixed wheels in rows and 3 in columns. It's the same for all of the other J1 matrices. Each row consists of the 3 terms in the 3 matrix from rolling constraints. J2 is a constant diagonal matrix whose size is the number of total wheels in rows and the number of total wheels in columns. And the entries of this matrix are the radius R of the wheel. For the non-slip conditions, these C1 matrices are derived from the kinematic constraints, and each row consists of the 3 terms in the 3 matrix from the equations of the sliding constraints. Thank you.